Now, going on to the PowerPoint slides, exponential functions, graphing exponential functions, equations with x and y interchanged, and then application of exponential functions. Graphing exponential functions. In Chapter 7, we studied exponential expressions with rational number exponents. That is, that they were fractions. What about expressions with irrational exponents, such as the square root of 2, let's say? Let's consider the rational approximation of r. That r is going to stand for the rational approximation of this. And as we put it into our calculators, we know that the square root of 2 is between 1.4 and 1.5. And as we keep adding decimals, we keep getting closer and closer. And we then say that the best expression of 7 raised to the square root of 2, that would be its exponents, is this. And notice we have 2, 4, 6, 7 decimal places. So any positive irrational exponent can be interpreted in a similar way. Negative irrational exponents are then defined using reciprocals, as I mentioned in our text lesson, as we will hear. So the official way of writing exponential function is, again, with our function symbolism, and then a to the x power, where a is a positive constant and a cannot equal 1, because 1 to any power is always 1, so that they exclude 1, is called the exponential function base a. So a is your base. So here they're going to ask us to graph the exponential function given by this. So again, they're showing us everything in one swoop. And here you recall from our textbook lesson, we make a t-chart where our x value will be this. So 3 to the 0 power is 1, anything to the 0 power. 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. Now, if our exponent is negative, let's just show you this. So 3 to the first power as opposed to 3 to the negative 1 power. Well, 3 to the first power is 3. 3 to the negative 1 power is a 1/3. That is, it's the reciprocal of 3. 3 to the second power is 9. 3 to the negative 2 power is 1/9. It's reciprocal. So this is what they said. And then, of course, we did this one, and the negative 3 power would be 1/27. Now, as we plot these points, we get the typical shape of an exponential progression. Now, they didn't plot to the 27th, that would be way up there. But you see what's happening. Now, if you recall from the textbook version where we did 2 to the x power, that one was similar to that. It went through 1, but it went out a little further this way. Okay? Now, 2 to the, or 4 to the x power would be, again, going through 1, but in a little closer this way. 5 to the x power would be in still a little closer. Now, a couple of things that we can look at on this chart here, on this graph, is that this x-axis, which is y equals 0, would be our x-axis. This is the horizontal asymptote. That is, this line will approach it, but never reach 0. Now, even though it looks like it's reaching it here, they're just making these big dots. Okay. Now, the reciprocal of 3 is 1/3. And if we raise 1/3 to various powers, notice what happens to our graph. Now, our points are just the reciprocals, and the graph looks like so. Now, if we put both graphs on the same, or both curves on the same graph, we then see sort of what's going on here. Now, our axis of symmetry, in this case, is our y-axis, and in a sense that would be dotted. And if you were to fold this over from the original, you would see that the curve is a reflection of y equals 3 to the x power. So as I mentioned in the text lecture, I would definitely make a picture of this. Now remember, if it were 1/4, the lines would be in a little closer. And if this were 4, this line would be a little closer as well. And let's go back because I want to review this with you as we look at it. Now, as we have a positive whole number here, and we raise it, as we increase the exponent, it has an increasing value. Here, as we increase the exponent on this side, when we have a fraction, it has a decreasing value. So these are some of the insights they want you to have in looking at this graph. Now, all of them go through the y-intercept of 0, 1, because anything to the 0 power is 1. Okay. And continuing with our summary here, all graphs of this have the x-axis as the asymptote. And remember, for our domain of our base, all real numbers but cannot equal a 1. And let's see here. These are a 1-to-1 relation, so its graph passes the horizontal line test. Again, tying it into some of the things we did in the previous chapter. Now, I went over this quite thoroughly in our text version. This is another way of looking at this formula in function form, plus k. And what it looks like is if you see something plus k, this will shift the graph either up or down depending upon whether this is positive or negative. This h here, though, this will shift the graph or translate the graph either right or left depending on the value of h. If h is positive, it shifts the graph to the left, negative direction. If h is negative, it shifts the graph to the right. And again, I'm assuming they're going to give us, no, they're not giving us an equation. We'll have to do that through practice. And then if you look at the text lesson, the textbook, they go over it in more detail there. All right, shifting equations with x and y. So let me just show you this. So normally we are having y equals some value a raised to the x power. Here what we're going to do is shift or interchange the x with the y, and we're going to see what the things look like. So there's what we've done. Now, when you plot these, and again, it's just using the t-chart, we're going to solve for y first. Well, 3 to the 0 power, where y is 0. In fact, let me write it right here. X equals 3y. If y is 0, 3 to the 0 power is 1. If y is 1, 3 to the first power is 3. If y is negative 1, x will be the reciprocal of 3, that is 1/3. If if y here is 2, 3 times 3 is 9, and negative 2 gives you the negative reciprocal. So we have enough points here to make our little graph. And notice what happens now. We get this. And what is this compared to what we had before? And it's not showing us this. So what we had before, let me see if I can sketch it in there. Was something like that. And I show this better in the textbook. They go over it in much more detail. So our axis of symmetry, which is x equal, well, let me put it here again. I got it the wrong way. Y equals x, which is this blue line. Shows that in a sense, and I didn't draw that very well here. Probably goes up this way more here. Let's see here. There, that's a little better. Okay. So it's a reflection and in a sense the inverse, which is what we talked about in section 9.1. Okay. applications of exponential functions, and that is when interest is compounded annually. Here is the formula. And if you had this much to invest at 5% interest, what would it be after, let's say, 6 years? And you would just put 1 year plus your interest, which is 5%. So this becomes 1.5 to the 6 powered, multiply it by this, and you get, wow, after 6 years, your investment is $80,000. You've made 20,000 just by having at 5%. And as I mentioned in my other textbook lesson, you don't get 5% interest anymore. It's a 0.5%, or the most you can get is like 1.2 or 1.3%. Hopefully the Fed will start giving us these nice interest rates again. So if we have money to put aside for years, and if it's going to be compounded annually, it really does build up. And you get what is called an exponential curve. Okay, well, there's a little brief thing. We're going to be doing some examples now, working them out for you.